Hello, hello. Welcome to this afternoon's session. I'm super happy and excited to be here and to have you all here. My name is Peter Moskowitz, and I work for Confluent. I lead a team that builds highly technical content, everything around Kafka and everything around Flink. And if you want to check out any of that content, you can go to Confluent Developer at developer.confluent.io and let us know what you think. I'm your host today, and I could not be happier to introduce our next speaker. Next speaker is John Fallows, who is the CTO of Acclivity. And with John, we go back more than a decade. There is no better person to learn real-time data and protocols from than John is. John was instrumental in creating an open industry standard that's there today on your mobile devices and every browser, the WebSocket standard. As John likes to put it, the company that he was leading was the one that put web into WebSocket. And I am very much looking forward to his MQTT talk. Before we get started, a few housekeeping items. This session is getting recorded, so within a week's time, this will be available online for you to all rewatch it or to share it with your friends. We are also going to take questions at the end of the presentation. I'll ask you to come to the center of the room and ask your questions there. And one last thing I would like to ask is this is your way of giving back to us, to the organizers of this to the conference, is by evaluating the session, letting us know what you liked, what you would like us to change. This is super helpful. And with that, I am super happy to hand it over to John.
Thank you so much, Peter, for that very generous introduction. It's wonderful to be here today, everyone. My name, as Peter says, is John Fallows. I'm originally from Northern Ireland in the United Kingdom, and about 25 years ago moved to California here in the USA. I am a serial entrepreneur. I've been involved in a few startups. Here at Acclivity, we're working on a lot of real-time protocols, and I have a deep background in that. As Peter mentioned, I'm a pioneer in this WebSocket space, helping to define both the wire protocol at the IETF and being instrumental in the JavaScript API design as part of the W3C for HTML5. I've got a lot of experience in messaging protocols, real-time protocols, including Java messaging, of course Kafka, including other things like gRPC and MQTT too. So today we're going to talk about MQTT and how we can integrate that with Kafka to scale it up. But first of all, what is MQTT? MQTT stands for Message Queuing Telemetry Transport. This is an OASIS standard that started out as version 3.1 and evolved to 3.1.1 and more recently version 5. It's been around for many, many years. And fun fact, actually, you might be wondering why it evolved from version 3.1.1 straight to v5, why no v4? Well, the reason is that when they did 3.1.1, they used the wire version 4 for 3.1.1 specification. And when v5 came around, they decided to align those, so they skipped straight to 5 on the wire and to the spec. In MQTT, you can publish and subscribe to receive messages. They could be text or binary. They are sent and received across topics, which live in a hierarchical topic space. So you can think of that a little bit like the files on your file system, a folder structure with hierarchy, and becoming more specific, from more general to more specific. The communication pattern between MQTT clients is a brokered architecture. So if two MQTT clients want to interact with one another over these topics, then they interact via the broker to communicate with the other client. There's no direct line of sight communication. So why do people use MQTT? Well, it's a lightweight and straightforward to implement protocol. It's pretty efficient on the network because it's so lightweight. The actual wire protocol itself doesn't use very many additional bytes to send the information. When the message payload is sent, only a few more bytes in the headers to get it to the broker and down to the other clients. So this means that it's using the network quite efficiently. As a result, the amount of processing necessary to consume these messages or to send these messages on the devices is also more optimal, using less power because there's less work for it to do. It's commonly used as a protocol to support interoperability between IoT devices, Internet of Things devices, and it's used in many vertical industries, including your smart homes, in cars, in manufacturing, and many others too. But there are some challenges with MQTT. For example, there's a lack of flow control built into the MQTT protocol itself. So whenever multiple messages are being sent in rapid succession, the underlying transport that sends the MQTT messages, such as TCP, is used to provide back pressure. This means that it's treated more like a file transfer, where there's a single sequence of messages being treated as one whole transmission, as opposed to lots of things happening in parallel over the same connection. And as a result, you can face sometimes things called something called head-of-line blocking, where multiple topics that are being published to in parallel over TCP, some of the packets representing, say, the first message may have been dropped and requiring retransmission at the network level, while the packets representing the second message may have already arrived at the server, but cannot actually be delivered to any receiving clients or even processed by the broker until the retransmission of those first message packets is completed. So in a sense, in that case, that first message retransmission is blocking progress of the second message. In terms of security, the MQTT protocol defers to the underlying transport to support encryption. So there's no payload encryption or anything like that built into the protocol itself. It's relying on transport layer security to encrypt the messages and the entire protocol as it flows across the network. And in terms of authentication for security, there are many different ways to authenticate into MQTT brokers. However, the standardization piece makes it clear where these authentication methods would fit into the standard protocol, but they don't define a lot of standard ways to do that. And of course, there are de facto methods that have evolved over time to support various different approaches, including JSON Web Tokens. From a scalability standpoint, obviously communicating between every MQTT client through some kind of centralized broker will bring its own limitations in terms of how much throughput you can get through this bottleneck in the middle. And we're going to talk a little bit about how to help to address that today. So architecturally then, if we were to compare the topologies of how MQTT and Kafka lay out, on the MQTT side, on the left here, we have an MQTT broker with a lot of different devices that are all publishing and subscribing to one another. And in Kafka, it looks similar from a very high level, a lot of Kafka clients interacting as microservices perhaps across Kafka topics, communicating with a cluster of Kafka brokers. Both technologies have the concept of topics, but they're a little bit different. In the sense of MQTT, topics are more like an attribute of a message. It's more like there's one large topic space, and each of those different topics are more like an attribute belonging to the message. Whereas in Kafka, the topics are more closely aligned with the underlying storage, and topics are broken down into partitions, and each of these partitions are guaranteeing order of delivery. In MQTT, order is guaranteed across the topic input and output. Also, MQTT has the concept of state, session state. So when a client connects to an MQTT broker, it can identify itself with a client ID. And when it does that and perhaps is abruptly disconnected, it can reconnect and recover from where it left off in terms of any subscriptions that it had made to receive messages from specific topics. Whatever progress it had already made, it can continue on from where it left off. And there's a similar kind of approach with Kafka, with consumer offsets and recording progress into the partition as you consume. But the idea of being previously subscribed and not having to resubscribe is different between the two. Another big difference between these is the intended number of connections and clients that are connecting to the messaging system. So in MQTT broker sense, we expect to have a very large number of devices When you think about, for example, Internet of Things devices, they're all very small and spaced out around your home perhaps, and around the globe, around the city, the smart city, your smart home. And as a result, the number of connections that you have to be able to maintain and interact with is quite large. Whereas in the case of Kafka, direct connectivity is typically more like direct line of sight within the data center, perhaps a little bit remote for cluster linking, but then it's more of a system level communication, more like a one-to-one from cluster to cluster as opposed to a very large number of independent clients. So if we want to integrate these two systems together, because you want to be able to understand messages that are arriving from your MQTT devices and get them into your Kafka broker so that you can then process them in some way, there are some options. And one option is to use Kafka Connect technology to tie these together. So Kafka Connect acts like back-to-back clients, where one client is connecting to the MQTT broker and the other client is connecting to the Kafka broker, and the messages are flowing across from one system to the other. And depending on whether you use a source connector or a sink connector, message flow can be in either direction. When you are thinking about what it means to then publish the message, it matters that the message has actually arrived in the target system. Since we have two independent clusters here, we have two different concepts of what it means to arrive into the system. So when a publish is completed in the MQTT broker, all that it means is that it has successfully arrived at the MQTT broker for further processing. It doesn't actually mean that it has yet propagated all the way through to Kafka. That's happening in the background, and it will happen in an eventually consistent manner, which might be quite rapid, but it's not the case that when the client receives the reply or acknowledgement that it has published the message, that that message has already arrived in Kafka. So there is a difference in terms of consistency between the brokers that's happening in the background to align those. An alternative approach to integrating MQTT with Kafka is to use an MQTT proxy that is making Kafka look like an MQTT broker. So there's only one storage in the architecture, that's Kafka itself, and the protocol transformation is occurring inside the MQTT proxy itself. So these devices that are speaking using MQTT protocol are blissfully unaware that Kafka's in the picture still. They feel like they're interacting with an MQTT broker, but when they do publish a message or subscribe to receive messages, the source of truth of those messages is in Kafka. And when a publish completes, that means the message has already arrived in Kafka. So this provides us with integration that still integrates the event-driven microservices that might be directly attached to Kafka to process and respond to MQTT devices. So how do you implement one of these MQTT proxies that needs to integrate these protocols together? Well, here at Acclivity, we have an open source project called Zilla that has an innovative approach to solving this problem. Zilla is a protocol transformation engine. It is able to think of all the different protocols that sit above the kernel. So thinking in terms of interacting with the TCP level sockets that delegate the underlying part of TCP to the kernel, or TLS encryption, or MQTT protocol itself, or even Kafka protocol communicating with the brokers. We think of all of these different protocols as a stream. And that means that it has a beginning, it has an end, we have data flowing over it in between, but they all have different flavors. And so these different flavors have different metadata associated with them. For example, an MQTT stream might have some information about the topic that it's trying to publish to. And when we try to communicate between different systems to tie MQTT and Kafka together, what we really end up doing is mapping the metadata. So the Zilla engine is designed to be very high performance. It's designed to be multi-core CPU friendly. It uses modern development techniques to align with the underlying hardware. It's written in Java, but it's more like system level Java. So we tend not to create any objects on the data path, so we're not introducing garbage that needs to then be collected, so we don't end up suffering from garbage collection pauses in very rapid data transfer environments. We tend not to put locks into the code base at all, so we have low-level cross-core communication techniques that use things like ordered memory writes to successfully collaborate across cores, but typically most of the data structures are single-threaded, and they stay in the same core by preference, so they don't need to cross over into a different one. So that allows us to streamline the processing and not have to spend time being slowed down by other cores waiting for a lock to become available. It's extensible by design, and we have added support for a number of different protocols over the years. So what does it look like whenever MQTT clients want to interact with Kafka? Well, they can send and receive text or binary messages. So when the MQTT client decides to connect and publish a message, say a text message, to Zilla, acting as an MQTT Kafka proxy, it's understanding the protocol at Zilla, turning that publish into a message that flows down a stream inside Zilla, and ends up being produced using the Kafka protocol directly into a Kafka topic partition. That can be for text or for binary. Similarly, when it's time to subscribe to receive messages, then the MQTT client can subscribe and get acknowledgement that it has successfully subscribed to an MQTT topic. And behind the scenes, Zilla is fetching messages that match that MQTT topic out of Kafka and delivering them to the MQTT topic, to the MQTT client. These MQTT messages can be text or binary again. So I'm going to take a brief departure from the slides to give you an example of how this works. So here we have some examples that are provided in GitHub in a Zilla examples repo that can illustrate a number of different characteristics of the Zilla engine. And one of them is an MQTT Kafka broker. This Kafka broker example is configuring Zilla to be able to behave as a MQTT broker using Kafka as persistence behind it. We package it up so it's very easy for you to get started. You just run the setup script to trigger creation of all of the containers in the Kubernetes cluster that's running locally. So I'll just start that up. So while that's starting up, I'll just show you the configuration. The configuration for Zilla is entirely declarative. We use a file called zilla.yaml. And as you can see here, it has some various different concepts in it, like vaults and bindings. We tend to think of the bindings as being those steps in the pipeline. In fact, I can show you a visualization of that. It's right here in VS Code. And you can see that we really have this kind of chain going from left to right. Let me see if I can zoom in a little bit here. So you can see we've got the TCP server and the TLS server, and we've got MQTT server. And you can see it's popping to the correct line in the configuration as we go. And then MQTT Kafka is proxying from MQTT protocol to Kafka protocol, and it's saying how to map that down onto Kafka topics from MQTT. Then we have a few other things here. We have Kafka cache, and we have the Kafka client speaking out towards Kafka. So let's go back. I think everything has started up. Yep, we're in good shape here. And so if we just quickly go to the README, then you'll see that we actually have all of the steps that you need to follow in order to run these examples yourself. So we're using the Mosquito client, and sometimes we use the K client to look directly inside Kafka. So what I'm going to do first is use the Mosquito MQTT client, open source one, and use that to subscribe to a topic called Zilla. And we have it in debug mode, so we're able to see some of the additional information happening here. The client sent no identifier, so one was generated on behalf of the client, and then it was used to subscribe to this particular topic, Zilla, and we got an acknowledgement that that was working. So now we go down, I'm just going to skip down to the publish one here. And you'll see that as we publish here, the reaction occurred immediately over in the client to say that it received a publish frame, a publish packet, it's called an MQTT, from the broker, which is actually Zilla, receiving that message, and the hello world bytes arrive successfully. So let's take a look briefly inside the Kafka that goes along with this to see what actually happened under the covers. So if we take a look at MQTT messages here, then you'll see that we've got the hello world message arriving in the MQTT messages topic. And if I click on this, you can see there's some additional headers in here and some timestamps and so on that are natural for Kafka. And if we look at the value, you can see it's hello world, and the key is Zilla. Okay. So just to complete this, I'm going to tear this down, and then we'll go back to the slides. Okay. So what did we really see? So the MQTT client is speaking MQTT protocol. So it sent a connect frame to MQTT Kafka. In this example, we're making it clear what the clients are to make it clear that they're different, distinct. So we put a client ID of client 1 here. And the MQTT client now receives a CONAC back from Zilla to confirm, to acknowledge that it has been successfully connected. Behind the scenes, Zilla had already been connected to Kafka and is acting on behalf of these clients. In fact, there's a connectivity offload between Zilla on the front end of a number of MQTT clients and the back end where Kafka is being connected to by Zilla. It's not a one-to-one relationship, so we're doing connection offload there. After it's successfully connected, the same MQTT client has done a publish packet to our Zilla broker, and it's identified what the topic is and what the format of the message is, and then the payload of the message itself. So when that is sent through, the MQTT Kafka proxy piece inside Zilla is transforming that into a Kafka client produce that is sending it to MQTT messages, and the key on that message is Zilla. There's some additional headers in here that also get sent. For example, we identify the different segments in the overall structure of that hierarchy of the message, hierarchy of the topic name for the message, so that we can understand the segments and apply wildcards very easily whenever you're subscribing. We also include this concept of a Zilla local header because there's a feature in MQTT or a characteristic of MQTT where you can say that you are subscribing no local. And what that means is that you want to subscribe to a particular MQTT topic, but you don't want to see the messages that you published. So the way that we approach that is to tag the messages that are published with who the local recipient would be. And then when you do subscribe, if you say that you don't want local, you want no local, then we filter out messages that are sent by oneself. So that client doesn't receive its own messages as required by the specification. We also include information about what the format of the message is, so that can be relayed to other clients as well. And the payload, obviously, is going into the value of the message. On the other side, there's an MQTT client. This one's client 2. It's also going through the connect-CONAC flow to successfully connect, but it's subscribing. So it's subscribing, and it's providing a subscription identifier to say that it wants to subscribe to a particular MQTT topic called Zilla. And it's received acknowledgement of that with subac to say that the broker will then send messages for that topic to the client. The message that was already in MQTT messages at this point arrives into the MQTT client as a publish frame, which you saw in the output of the demonstration, and that's annotated with the subscription ID that was used for the subscribe. So if different clients had come in looking for the same message but providing different subscription identifiers, they would see their own slight variation of the publish frame, publish packet coming down to the MQTT client with its own subscription identifier on it. And the payload arrives all the way through, of course. So as is typical with messaging systems, this could be happening while both clients are connected in live, or it could be that the producer in this case MQTT publisher, is publishing the messages ahead of time, and the MQTT client is catching up after the fact. There is a concept of a retained message in MQTT, where if you mark a message as retained, then it should be replayed when the client subscribes. And if it's not marked as retained, then the client's just picking up live messages. All of that is supported. So, of course, when you put the MQTT proxy in front of Kafka, you see the messages all flow through Kafka, and you can observe everything that's going on. But you can also do a little bit more. So now that you've maintained this illusion that Kafka looks like an MQTT broker, you're able to switch out either side. So one possibility is that you want to have an event-driven microservice that is subscribed to a Kafka topic and wants to process all of the inbound messages coming from an MQTT client. It could be sensor readings for temperature or something like that. And with this approach, we're able to do that because we are able to map the Kafka message that's coming from MQTT into the topic, and now the event-driven microservice is able to process that. It could be doing analytics on that, or it could be choosing to cause some other part of the event-driven architecture to be triggered for some additional behavior. In addition to that, the event-driven microservice could also be intending to interact with the device. So rather than receiving messages coming back from a particular MQTT device, it could be that you need to send it a command of some kind, perhaps to tell it to reboot, or perhaps to tell it to download an over-the-air update, or something like that. So in that case, the MQTT client needs to be subscribed over MQTT to Zilla, and it's sitting there waiting for a Kafka message to show up, and that's where the event-driven microservice comes in. It understands there's a need for this to be sent to the client, and it can be sent to Kafka, and then the Zilla will react and deliver the message down to the MQTT client, just as you would expect. So that's the functional stuff, but let's talk about scaling. There are a few different ways to scale. You can scale up vertically, where you're just adding more processing power to, say, a single instance of Zilla. Of course, when you do that, you often add additional CPU cores to the underlying deployment. When you do that with Zilla, we take very good advantage of those additional cores because it's designed to be multi-core friendly. Another aspect of scaling up is that I mentioned briefly earlier this connection offload that's happening in the background between Zilla speaking to Kafka with a small number of connections versus perhaps a very large number of MQTT connections coming in the front. And when you do that, that means that you're pulling messages from Kafka once on behalf of many. We understand the importance of maintaining the ordering guarantees of message delivery over MQTT. So that's why you saw that the key in the MQTT, the key in the Kafka messages earlier was the actual MQTT topic. So that means that we were able to guarantee order because that key gets hashed to the same partition each time. So all messages for the same MQTT topic arrive in the same partition of the same Kafka topic, so that ordering is still guaranteed. So for each partition then, as the cache is being populated, we're doing that with one core in the back of the Zilla engine and writing into the cache, but we're able to consume that from multiple reader cores on the front. So we get this kind of internal fan-out effect that's occurring inside the Zilla engine itself on that pipeline. And not only that, but when we were talking earlier about the statefulness of MQTT, we do support that stateful session capability to know the subscriptions that you had previously subscribed to from an MQTT client that was then abruptly disconnected and had to reconnect and recover. That means that we have to be able to tell when the client comes in what its session state was. And also there's an interesting aspect to that where if a client thinks that it's disconnected due to some network failure, but the broker, the server side, has no idea that it's actually disconnected because it hasn't completed a heartbeat to know that it didn't get a heartbeat response with a ping pong. If that hasn't occurred yet, then there's this inconsistency between the client's view of the world and the MQTT broker's view of the world. And because of that, when the client reconnects and it represents the same client ID, then the rules in the specification say that the MQTT broker side has to discover that there was an existing session with the same client identifier, close that out, make sure that it's not being used anymore, before responding with that CONACT to the new client to say, now you can continue as this client ID. And that's pretty straightforward within the context of a single process. But when you start trying to solve that problem, when you scale out, for example, across multiple Zilla instances, then it gets very complicated unless you are able to rely on something behind those instances to coordinate. So we did do some work with integrating this concept of MQTT sessions with Kafka consumer groups, where each client identifier is in exactly one consumer group. So then there's one member within the group, and whenever a new client comes in, it can detect that and switch over to the new member being the leader of the group, making sure that the old one got torn down, and before we continue. So that means you can even observe the progress of these consumer groups behind the scenes using standard Kafka tooling. One of the implications of that, typically, is that for traditional consumer groups, you would be heartbeating from a Kafka client at a reasonably regular interval. So when you multiply this up by a very large number of clients, then you want to have a solution for not overwhelming the back end with a very large number of clients producing a very large number of heartbeats at a very frequent rate. So what we've done there is we've optimized the way that the heartbeat works to be more proportional to the session lifetime for the MQTT client. And when the MQTT client requests a specific session expiry, we make sure that that falls within the min and max range as defined by the Kafka broker itself, with a preference to go as close to the max as possible. And then during these interesting session takeover interactions that I mentioned, where there's this disconnect between the view of the world of the client and the view of the world of the broker, where the new client reconnect has to take over, when that's happening, then we have a different signaling mechanism that allows that to progress more immediately without requiring us to do very more frequent heartbeats just in case. So that allows us to scale up. And not only that, and scale out, not only that, but whenever you have a lot of different heartbeats going at once, you don't want to have a separate connection dedicated to each one of these heartbeats, of course, each one of these clients. So we have connection pooling out the back to support that. With the session state, when you scale out, there's also a desire not to replicate the entire session state for all clients to every single instance. Because now, as you're increasing the number of instances, presumably with the intention of increasing support for the total number of MQTT clients, there's going to be more and more session data as there's more and more clients. And so if we don't separate the data in some way across the instances, then that's not going to scale as well. So what we've done there is we've added the concept of a consumer group to this MQTT sessions topic, where we store the session state for a client. And based on the number of different partitions in that topic, we're able to hash the client identifier to one of the partitions in the MQTT sessions topic and treat it as a sharded topic space. So depending on which instance you arrive at as a particular MQTT client, you might discover that you're at the quote-unquote wrong instance. So you arrived on instance 1, but your state for your client identifier is really over on instance 2. In that case, we have support for something called server redirect in MQTT specification, and that allows us to send the client to the correct instance of the Zilla cluster, if you like, that allows it to find the right one where the session state lives. And that also means that we can guarantee that the client is arriving back at the right one each time so we can scale out. And as we shard out the number of sessions, we're growing the capacity without making the scalability or the performance of an individual instance any less. The benefit of that, of course, is really important as you scale out horizontally. And we've talked about scaling up vertically, but there's a bit more here too. What if you want to scale geographically across different regions across the planet, globally? Well, in that case, we think that Kafka itself is extremely well suited to any kind of replication across regions that might be necessary to be able to get the right messages to the right places, but not every message to every place, so that you can target your data flows and get the efficiencies of getting the data to where it really needs to be for whatever your application needs are. When you use Kafka for that, that means that any mapping to other protocols that you want to support needs to happen at the edge, because there's Kafka closer to that edge, and then the mapping to the other protocol is also at the same edge, mapping to the local broker. That means that you also want to integrate authorization at the edge, where you can authorize your MQTT clients. And in Zilla, we have first-class support for TLS client certificates, for mutual authentication, and also for JWT access tokens. And with JWT access tokens, it's not just you're authorized or you're not. There's also an opportunity to specify some individual privileges in the scope claim, and we can apply that inside the configuration to say, if you have this privilege, then you're allowed to subscribe to those set of topics. Otherwise, maybe you're only allowed to subscribe to these other ones, or publish to them, or so on. We can also validate that MQTT clients are sending valid messages into these MQTT touchpoints with Zilla at the edge. Now, if you want to do that, then you need a way to specify what a valid message means. And there's a relatively new standard that's coming out. The version 3 is imminent as we speak, called Async API, that's used to describe the contract of these asynchronous style protocol APIs. So you might be familiar with OpenAPI for REST, where you're able to lock down the paths and the methods over HTTP and the structure of the messages that are being posted or received over HTTP request response. Well, this is very similar, but it's dedicated to protocols beyond HTTP as well, including MQTT. So here's an example of just such a contract. Async API specification allows us to define these things. And you can see on the right that we've got the schema section, which is defining an item that has some properties with the ID and status, and which of these fields are required. So what does this mean in practice? This means that with that configuration in place, we can say that the MQTT client might be publishing messages into Zilla, and it could be that it's required to be a text message, perhaps with a particular encoding, or straight binary message, perhaps with some kind of length limitations, and also perhaps a structured message. And in each case, we can apply the validation to make sure that only valid messages make it through. And in practice, this means that you only have maybe not only, but you're more likely to have only valid messages into the target system, such as an MQTT broker behind the proxy. So with that, I'd like to show an example of how to use Async API in action. And we'll just head over to Visual Studio because we have another example under Zilla examples here. So this is where we have a MQTT proxy for Async API, where Zilla is acting as an intermediary between an MQTT client and an MQTT broker. So I'm just going to quickly start up that example. And once again, it's very easy. If you check out the Zilla examples project, you're able to get up and running with a single click here, single command. And we'll just quickly take a look at that Async API. So one of the things that's coming in the Async API 3 work is to complete the VS Code extension update so that it will support 3.0 natively. That's why you see some errors here. But you can look down here, you see we've got some channels. So in async API, there's a general concept of channels, which in MQTT world is a topic. And we've got this indication of the types of messages that are supported by that. And so there's an item in there which is coming from the schema down at the bottom here. And this is the same schema that we saw earlier. So I believe that's all started up. Yep, we're good. And so now I just want to show that we have an ability to take the async API that I just showed you and use it to generate a configuration for Zilla, the Zilla.yaml syntax that I touched on earlier. So here you can see there's a very small Zilla.yaml file. It's listening on TCP, and it's got MQTT awareness as well, and it's got this content that's being enforced for a particular topic, and it's enforcing that as a JSON structured message where it understands the schema to be used to enforce the structure coming from a catalog. And a catalog definition in this example is an inline catalog that defines the schema, and you can see here that it's defining the same set of properties with the same required properties within the object. So with that in place, we're going to go ahead and show what happens. So there are two different MQTT endpoints here, remember, because there's the MQTT broker that's sitting behind Zilla. That's listening on port 1884. So we're just going to subscribe to that. And then we've got Zilla sitting in front, which is acting as that intermediary to enforce correctness on some of these types, for example. So first of all, we'll publish a valid message. So this is sending a message with JSON message with two properties, ID and status. And so when we publish this to port 1883, which is the default, which is why we didn't have to do this -p argument here, then it ends up sending it through Zilla, and it makes it through to the back end because of the valid message. However, if we take a different message and send it, then you'll see here that we've changed the name of the second property from status to stat. And you'll also notice that we added this repeat with a repeat delay. The rationale for that is that the Mosquito pub client is kind of finishing up too early. It's not waiting for the acknowledgement code to give the error. So we send repeat, we let it wait, and it sees the error message. So now we try to send this, and you'll notice that the message did not come through. So I'll just make that even more clear. Send it again, nothing came through. And if I go over here and set this to status instead, and we don't actually need to repeat anymore once we make it real, you can see that it came through successfully because now the structure of the message is correct. So this is how we can apply validation to messages at the edge before they get to the next hop in the architecture. And of course, I showed it here with an MQTT proxy, but the same ideas hold, same configuration holds whether you're doing MQTT to MQTT or MQTT to Kafka. So all the examples that you saw here today were on the Zilla examples repo that you can check out from GitHub. We'd love it if you check them out for yourself, you try them out, and if you have any feedback, we'd love to hear from you. There's another variation of the Kafka broker example, MQTT Kafka broker example, that includes JWT and some privileges that are being enforced in the configuration so that you're only allowed to publish and subscribe if you have the valid claims. And the async API example, of course, is there too. But we talked a lot today about MQTT and Kafka in Zilla, but Zilla is not limited to those protocols. We have support for a number of different protocols, including gRPC and REST as well. So if you'd like to see some of those in action, please make sure that you stop by the booth where we're running the Zilla taxi demo. And that taxi demo is also available from our GitHub repositories within the Clivity organization, so you can check that out later as well.